So we have a confidence interval for the ICU patients that had an infection, the proportion that died, different from those patients that didn't have an infection and died. We did the stat key simulation that said, on average, the difference is about 14, 15% here. And the simulated confidence interval said that the range of differences is going to be somewhere between 3.2%, meaning about 3.2% more people with an infection died than didn't have an infection, but it could be as high as a difference of 26.2% of more, 22.6% more people died if they had infection than not. The central limit theorem formulas that we applied in the spreadsheet were pretty close to these values, 3.26%, 26.3%. They're in the ballpark of each other. So again, that's the range of differences that we expect to find in the proportion of people who died with an infection than not with an infection. So thing to note here is that 0 is not in this interval. So this confidence interval suggests that there is a significant difference. If there wasn't a difference in the actual population, we would find 0 in our interval, typically. Didn't show up there. So next thing we want to look at is how to do a hypothesis test with 2 different proportions. Another thing to note is the standard error in this simulated sampling distribution was about 0.059 versus the theoretical formula for standard error came out to be about 0.0588. And remember, that's kind of a wicked formula here. This is the formula for the standard error for the difference in 2 proportions. We have to combine the variation we see in one population with the variation we see in the other population. And this is the formula we do that with. Next, we're going to try and do a hypothesis test on this same set of data. So back to the data for a moment. So I took this data from the StatKey library. It's ICU admissions, 200 patients that were admitted to the ICU. I selected the variable status, which is did they live or die. 0 means they lived, and 1 means they died. And in the ICU, did they have an infection? 0 means they did not have an infection. 1 means they did have an infection. And then I summarized that data in this table right here. So just grab that again. And this time we're going to do a hypothesis test. So for a hypothesis test for a difference in 2 proportions, we assume as the null that there is no difference. So again, difference in proportions. 2 populations. So I'm saying population 1 is the people in the ICU with an infection. Population 2 is the people without an infection. So my P hat 1 in this case is the 24 people who died out of the 84. That was the proportion with an infection. And then we have my P2, my other population was the people in the ICU without an infection, and 16 out of 116 of that group died. And again, this gives us the proportion without infection. Who died? We're trying to test, is there a significant difference in these? And anytime we ask a question like that, is there a difference? The null hypothesis is no, there's no difference. They're about the same. So for the null hypothesis, we assume that P1 equals P2. So proportion 1 is equal to proportion 2. Sometimes we write that as the difference in proportions. So alternatively, I guess I won't write alternatively because I need the alternative hypothesis, but sometimes it's going to be written as P1 minus P2 is equal to 0, right? So this says they're the same, which means there's no difference. Same proportion, no difference. Right, the difference is 0. Oftentimes they'll take that P1 minus P2 and call that difference just P difference. How much are they different by? And just let's look at our sample. This is for the population. We're assuming in the population there's no difference. Every sample is going to be a little bit different. So I took this and put it into my spreadsheet where I do all kinds of normal calculations, and I just entered my X1, 24 out of 84, and 1 had an infection, and calculated the proportions down here. So we get about 28.6% versus 13.8. 28.6% versus 13.8%. This one's about double that one, so that seems pretty significant, but we really need to measure it with a hypothesis test to double check. The difference in those two, I also calculated in that spreadsheet, is about 14.7. So we have a difference, that would be P1 hat minus P2 hat of about 14.7% is what we're claiming the difference is. Now, by the null hypothesis, there isn't a difference. So if I did a whole bunch of different samples like this, on average, I should find that when I took P1 minus P2, I got about 0 on average. So some should have given me a -% here instead of a positive. So it should be a lot of variation there. If there's no difference, again, then when I take P1 minus P2, I get 0, and I can't work with 0 directly in terms of the formula for a z-score, a t-score. So here I need a z-score, and the z-score is typically the sample stat minus the null hypothesis value divided by the standard error. And when we did the confidence interval, we used the P1 hat and P2 hat. The confidence interval assumes there's 0, which means this is a 0, that is a 0, and then I've got a bunch of zeros used in the calculation down here, and everything's going to fall apart with all those zeros. So we got to tweak it a little bit. If they really are equal, then I can just take the total amount of people who died and divide by the total amount of people there, if there's no difference. So that's what we're going to have to use when we're calculating the standard error for a hypothesis test for a difference. So that's what we call just P hat with no subscript 1 or 2. And it's just x1 plus x2, right? Take all the people who died, divide by how many people there were, because there's no difference whether they had an infection or not. That's our assumption. So here, that's going to give me 160 out of 200 when I put it all together. And I need that number to get my standard error. So my standard error is going to be kind of like the standard error for the confidence interval, except now I'm assuming there's no difference. So this is what my P is. So that's that P hat times 1 minus P hat over the first sample size, and 1 plus P hat times 1 minus P hat over the other sample size, and 2, and we take the square root of all of that. And this is a good place to whip out a spreadsheet to do that instead of a handheld calculator, because then we can reuse it, which is kind of cool. Let's hop off to a spreadsheet to continue this further. So I started here, another tab, to proportion hypothesis test. And in here, I wrote it up in a couple of different ways. The hypothesis could either be P1 minus P2 equals 0, or we could write it as P1 equals P2. And this is the more common way to write it there. But I just like to talk about that the idea of being the same means the difference is 0, right? There's no difference. The alternative is either going to be that there is a difference, that the difference isn't 0, so there is a difference, right? They're not the same, or one's less than or greater than the other. So these are the options for the alternative hypothesis. In this one right here, I'm just going to say they're not the same. P1 I have here from my data, and then here I calculated P2 from the data, and see, that's not the right data, so let's plug it in. What do we have here? We had 24 out of, was it 84? And then 16 out of 116. So we put that data in, let's double check I got it right. 24 out of 84 for the infection, population 1, 16 out of 116, no infection, population 2. Okay, so we got that in there, population 1, population 2. Other things we need. We need to know the difference in those two. So there's my 14.7, or it's really 14.8, I didn't round right. Let's fix that. See, we all have rounding error issues on occasion. And then I have the pooled proportion, so that's when I just add up x1, x2, right? So back here, those two added is my 160 out of 200. And that does not look right. Did I make a mistake? I have an error. 160, holy shit. That's not 24 plus 16. Okay, I do have a mistake here. Oh, I got these guys switched. Must have moved stuff around at some point. All right, delete. There's the 160. Notice that. Human error. Add those up. All right, let's double check. 1624 is 84, that is true. 116 is 116. Okay, now that looks better. Let's fix the notes here. Those two numbers get switched. Thank you for noticing, good job. All right, so 40 out of 200, 20%. That looks more like it. All right, and then I have n here. So these are the things I need to create my test statistic. So back to my notes here. So the test statistic is my sample stat, and my sample stat is what I found for the difference in the two actually in my sample. So in this case, that sample stat is my P1 hat minus P2 hat. The null value for a difference assumes that there is no difference, right? The difference is 0. And then that standard error is this wild formula over here based on this pooled proportion. All right, so in my spreadsheet, again, I entered my sample data. I got P1 and P2, so I could get the difference. I needed P1 and P2, so I get the pooled proportion. Actually, I needed X1, X2, N1, N2 to get that. All right, so I highlight information that's given for the problem, and then there's all the other stuff I had to calculate. So I had to calculate the difference in those two sample proportions. I had to calculate the pooled proportion. I needed to grab the total sample size in there. And the standard error, that's that wild formula that I was talking about, where we just use the pooled proportion and the individual population sample sizes. So we're getting a standard error of about 0.0573. And reminder, that stat key one I had done earlier. Let's go back a page, where did I put that? Forward a page over here. Stack, he said it was about 0.059. The confidence interval said it was about 0.058. So notice they're all in the ballpark of each other, and that ought to happen because of the central limit theorem. All right, so back here, we have everything we need to make that z-score. So let's see what the spreadsheet says about it. And again, the z-score, I just take, since the null hypothesis is 0, it's basically the sample statistic, the difference in the proportions divided by the standard error. It simplifies quite nice there, finally. And my z-score is 2.5788. The z-score is more than 2. That's typically considered unusual. I chose to do a two-tailed test here because I'm saying, I think there might be a significant difference, right? That means not equal. And the two-tailed version gives me 0.0099. So about 1% is my p-value. And to find that, I used the norm dist for the left tail and doubled it. That was the easiest way to go about it. And I had to do a little mathematical jiggery-pokery on that. I'll draw a picture as to why. New page. All right, so here's what we got picture-wise. Usually, you've seen me do this before when I'm doing a hypothesis test. In the middle goes whatever the null says. And the null says that the difference is 0. There's no difference. I then calculated a z-score for my sample. So my sample statistic, p1 hat minus p2 hat, that ended up being around 0.01477-ish. I need to know how far that difference is from a difference of 0. And the z-score to go with that was about 2 points, what was that again? 5, let's call it 2.579, 3 decimal places. So 1 standard deviation, 2 standard deviations, 3 standard deviations, mine is somewhere out here. So that right there is a z-score of about 2.579. That's how far my difference is above a difference of 0, right? We can see here that's going to be outside our 5% confidence, our 5% significance level. But I do really want to find that p-value, which is the chance of getting a higher z-score from that from a similar sample. And to get that p-value, that's where we use that norm dist formula. And my spreadsheet calculator says it's about 0.0099-ish, which is around 1%. And I did not have a significance level picked yet. So let's go with a significance level of 5%, the standard one. This is about 1%. It's definitely less than alpha at 5%. And so this would say, hey, that's pretty low p-value. The null should go. So we're going to reject the null here. So the null value said there was no difference. That means, so this is my decision. My conclusion would be there is strong evidence that there's a significant difference in these death rates. This is a conclusion. There is significant evidence So, and again, I didn't go for a right tail to say that there's, they die, people with an infection die at a much higher rate. I went for a two tail. So that's why that's going to have to be my statement. And actually, I don't want to use the word significant twice. So let's use strong here so it reads a little better. So there is strong evidence that there is a significant difference in what? Good question. Difference in the proportion of people with an infection in the ICU who died to the proportion got to say what difference I'm talking about here. Of people without an infection. In the ICU, who died. We are concluding there's enough evidence to say they're not the same. This is too far from no difference for there actually be no difference. So the null hypothesis, there's something wrong with it. People with an infection are dying at a higher rate. What can we do about it? That's a whole nother story that the hospital's got to deal with. Thanks for playing.